Here's a quick video tutorial walking you through how to convert your measured UV-Vis absorbance of your perovskite thin film into an estimate for the band gap energy of the material. First, open up the data analysis template and choose the UV-Vis band gap tab at the bottom. And the data should look something like this. This is pre-established data, so you'll need to delete and add in your own data. There's only two columns of data, D and E here, that you'll need to populate from your own measured UV-Vis absorbance. So you'll need to replace the wavelength data in nanometers with the wavelengths that you measured over and the corresponding absorbance here. The rest of these columns, F, G, H, and I, are computed automatically. Be sure if you are replacing these data that you are making sure you don't have any excess data at the bottom, meaning the number of rows is consistent across all of these columns. If you have more or less, you may have to drag down or delete excess. Okay, so the absorbance value will be computed into an absorption coefficient using the film thickness. This is not going to matter. You can leave this at 1 centimeter. That'll allow you the computation of the absorption coefficient and then the photon energy from the wavelength that was measured. And then you have two different types of electronic transitions in semiconductor materials, either the indirect band gap or the direct band gap. For the majority of the materials that you will be investigating in this course, you'll be looking at direct band gap, so you can neglect the indirect unless you have reason to believe this is the type of fit that you'll need. So these are essentially linearized equations of the absorption coefficient for the material, which allows us to fit a straight line and then extract that straight line to compute the band gap energy. There's several different methods. These are just estimates because UV-Vis absorbance is not the best way to measure this. It's not the most accurate way to measure this, but it is the easiest and by far the most common. So here we're talking about estimates of the energy and not necessarily exact measurements. So you can choose which method gives you the best results here. The first one is the simplest, and that requires actually no computation at all. We just plot the absorbance spectrum, so absorbance on the y-axis as a function of the excitation wavelength here. But you can see that I'm only plotting a portion of the spectrum from 700 to 850 because I'm interested in this little rise right here, which is the band edge of methyl ammonium lead iodide. So you can see this slight increase in the absorbance right around between 800 and 760 nanometers. And the exact onset of when we see this increase, if we were to extrapolate that down to the x-axis, that would give us the exact band gap energy. So as an estimate, because we're not determining precise values here, you can just take a line, this green line, and just overlay it on this region of the curve, and then an orange line and overlay it with the step or the increase in the absorbance. And where these two things, these two lines intersect, we can then have a third vertical line, this red line, trace it down to the intercept. This would give us a value of 790 nanometers, which we can convert units of wavelength into energy, which gives us 1.57 electron volts. If we scroll down, we have method 2, which is called the talk plot. That's where these computed values of the fits come into play. So with the talk plot, you'll make a graph of the direct band gap fit, especially for perovskite materials. So you'll take this column as your y-axis, this direct band gap, and plot that as a function of the energy in electron volts, which is the photon energy, this column G here. That'll give you this full blue line plot here, but we're really only interested in the region 2 to 3 electron volts. And so what we can do is plot a second series of data. So in the data source, that would look like, here's my original series, which is the full plot. Here's my second series where I'm only plotting my 2 to 3 electron volt range. So I'm plotting of the photon energy only the 2 to 3 electron and the corresponding direct band gap fit for that. So I'm essentially replotting every data point of the blue line, but only from 2 to 3. What that allows me to do then is to take that series of data and fit a trend line. And so then the trend line gives me this equation of the line here, and I'm specifically interested in where that straight line that's fit from 2 to 3 electron volts intersects the x-axis. So to find the x-intercept for an equation, that's when y equals 0. So I would just substitute 0 in for y here, solve for x, and you can see that I just typed in an expression here where I just used the intercept here, the y-intercept, divided by the slope. Because I'd set y to 0, that gives me this intercept. That gives me 1.58 electron volts, which is the same as where this green line would have intersected the x-axis. So from method 2 I get 1.58 volts, from method 1 I get 1.57 volts.